Hello everyone and welcome to a new video in our firmware series. We continue with the topic buffer overflow, and this is part 2. In the previous video we explored how to use the buffer overflow vulnerability to modify the value of a local variable. In this video we will dive into a scenario I called hijack the execution, where we force the firmware to deviate from its intended execution path and jump to a function of our choosing. As usual, we begin by reviewing the C code, which I think it will make it easier to understand. As you can see, here is our C code that represent our firmware. We have the main function which calls authenticate user, which subsequently call user. However, now we notice here there is a buffer overflow vulnerability because scanf does not check the length of the user input, which allow the user to overflow the buffer, which is in this case the user role 32 bytes here. Another point to notice is that the function call admin, which grants a shell on the system, as you can see here, is never called. So our task in this video is to hijack the regular execution of the firmware and force it to call the function call admin, thereby obtaining a shell on the system. To do that, let's jump to our friend GDB. I already prepared the firmware here, and I start GDB. The first thing to do, I will disassemble main here, and nothing special happening in main. We have a call to the authenticate user, so I disassemble authenticate user here. Let's analyze a little bit the authenticate user, and there are a few points I want to mention here. So as we know now, the first two line, it's a function prologue, which will set up the frame of this function. Then we allocate memory, and in this case 32 byte for the user role variable. Then here we have this is a call to the printf, and edi register is used to pass the argument, and then we have a call to scanf, and the register RSI and edi, both of them are used to pass the parameter to scanf. And at the end here we have the function epilogue. I want to mention two things here. The leave instruction, as we seen at the beginning that the RSP is stored in RBB. Now we do the opposite because we want to clean up everything and go back to the state of the stack before calling authenticate user. So that's why RBB will be placed in RSP, and then we pop RPB from the stack, and then we reach to the return instruction. And what this instruction does, actually the value pointed to by the RSB will be put into the RIB, or the instructor pointer. So this is very important to note, and we will see that in our video later. Another point I want to mention is calling another function. So now we see in the main function it calls authenticate user. However, there are specific steps that we need to follow. The first step, I summarize it here in main. Before calling authenticate user, we push the address of the next instruction on the stack. What I mean, this is the next instruction, so this is authenticate user, start here, and this is the next instruction. So before calling authenticate user, this value will be pushed on the stack. After that, we will jump to the first instruction in the authenticate user, and the execution of this function starts by pushing RBB and then move RSP to RBB and allocate memory to the local variables. So it's very important before calling a function, the address of the next instruction will be on the stack, because this will be used at the return address. After execute user function is finished, then you need to return to return address, and then after that the next step is the execution of the function authenticate user. So here we can a little bit visualize the stack. So here first push return address on the stack, then push RBB on the stack, and then push the user role array on the stack. This is how the stack looks like. Again, this is higher address here, lower address. So we move toward the lower address, but when we write from lower address toward the higher address. So this is how the stack looks like. Okay, let's see that in action. Let's get back to our GDB. I will close this one, and let's go here. The first thing I will do is to set up a breakpoint at the authenticate user. Then I will run the program, and then I will disassemble authenticate user again. So we are exactly here, the stack at the sub instruction. So now let's analyze the stack at this point, and you can see now the stack is at the address ends with the DDE0, and it contains the value which end with DE110. Actually both now the RBB and RSP the same at the same address, and both of them have the same value. What's interesting now is let's run the same command, but let's add 8 to the stack pointer, and now we are at address ends with DDE8, and then we have the value B91140. Do you remember this value? We have seen this value here in the main function. Actually this is the next instruction or the return address, so it's already pushed on the stack. What's next now is let's run just one instruction. So next we are now here at the move, so RSP -20 is executed. Let's see the stack here. So DDC0, this is the address of our user role variable array. Okay, now I will do something else. I will set another breakpoint after the scanf. So after we receive the user input, let's set this breakpoint here, and then continue the execution. When the program asks me for the username, I will provide 4, 5, 6, 7, 8 A's. And now let's examine as usual the stack at RSP. So what we see here, this is the address of the array user role. This is our 8 A, 41, 41, 41. Then here we have at the DDE0, we have the value of the RBB, and here we have the address of the next instruction. Let's again visualize that, and I prepared something similar. So let's compare now here. Okay, so at this address RBB -20 hex, which is ends with DDC0, it's here. Here we find our 8 A's. So this is the user role. Then at the address ends with DDE0, here DDE0, we have our RBB here, and this is the value DE10. And at the address DDE8, here is the return address, and here is the value. I just another way to visualize how our values are stored in the stack. The buffer here the RBB here, and then the next instruction here. I hope that give you a little bit understanding and visualization of how all these parameters or values are stored on the stack. Okay, now our next step is to craft the payload. Let's close this one and get back to GDB, and let's see. Okay, what do we need for our payload? We need 32 of A, this is for the user role, then 8 of B, this is for RBB, and then we need the address of call admin. Actually, we can get call admin, and you see this is the first instruction in the function call admin. So this is would be our payload, user role RBB plus the address of call admin. Let's try it. Let's give it a shot. This is I prepared here, but first maybe we need to, let's see if we have a info breakpoint and we have an address. Okay, so now let's run it and let's examine the stack. So we see the A's covers or our buffer, there is a role, then we have the B's for the RBB, and then here we have the address of call admin. So everything looks fine on the stack. So that's mean if I continue the execution, we should see that a shell is forked. So let's do that, continue. However, I see that my program stops here and it doesn't continue. Even if I say continue again, it will not continue. And what I notice here is not aligned to 16 byte, even though you see here you are the admin. So what is the issue here? Actually, in some distribution, the stacks need to be aligned to multiple of 16, and here because we are calling a system in let's say not the standard way, that's mean there is now misalignment in the stack, and that's why when here in the call to the sys system bin sh, we will have an issue, let's call it the alignment problem here, and that's why we will not get a shell here. How can we overcome this obstacle here? Actually, there is a way to overcome the stack alignment problem. What is this way? The idea is that we need to subtract from the stack another 8 bytes. How can we do that? We search for an instruction which does that for us, and one such an instruction is the return instruction. So what I did, I went back here to our main function, which has a return instruction at the this address. So I took this value and we added to our payload. So now our payload is user role first, then the RBB, then here we have the return instruction, then after that the address of call admin. So before calling admin, we added the return instruction. Let's see if this work for us. First, maybe let's set again our breakpoint here. Now I will use the second payload I prepared. Let's run it here and let's observe the stack again. So everything similar, and instead now here we have the address of the return instruction in the main function. Then we have the address of the call admin. Let's run it. Maybe first let's take a breakpoint at this address, and I will show you. Let's continue now. And where are we now? We are at the return address of the authenticate user. So if for example, maybe it's better to see it disassemble authenticate user. You see, we are exactly here at this point. So we receive the user, we call user input, we call the user, and now we are exactly here. Let's run just one instruction. Where we will be at the main. You see, we are you can look actually on the RIP instruction. We are here executing the return instruction from main. Let's run another next here, and you see now I am call admin. So instruction pointer pointing to the first instruction, push RBB on the stack. Let's disassemble call admin, and exactly you see we are here. Now if I continue the execution, you should see that or we will see that a shell is spawned because by default GDB will follow the forked. So that's why you will see, okay, let's run it maybe first, and you can see here that process this number is executing now a new program. If I do ps-b, and for this process you see it's a shell running here, so that's mean our program execute a shell here. Let's see how we can perform this the same but outside GDB. I will take this value, I will exit, and so it's the same payload we prepared, but now I will point it to another file. Let's call it payload pin, and let's first try that I want to redirect this payload to our function. What do we see here? We see that you are the admin user is printed on the screen. We see some error, and even we see segmentation fault here. Why this happens? Actually because either if I'm using payload and pointed to the firmware, or even if I use directly the payload and I pipe it to our firmware, we will have the same issue. The problem is because the pipe or the redirect will send end of file to the scanf, and that's why the shell will be closed. One way to overcome this obstacle, again, we can use cat payload and then hyphen, then bybit now, and our firmware. Let's see what happened here now. What's your name? Whatever you write now, you are getting a shell. You get a shell on your device. So this is one way. If you are ever in this situation and the pipe doesn't work for some reason, you can try this one. There is another way. Actually, we can do also cat payload, and then cat again, I close it, and then I pipe it to the firmware, or whatever, and then you have your shell on the device. So we managed to force the firmware to call a function that present in the code but was never called, and the call, I will call it the call admin. We force it to be called, and by doing so we got a shell on our system. Thank you again for your watching. I also hope you learned something from this video, and we continue in the next one. Bye bye.